Okay, let's unpack this. When you think about steel, do you ever consider how it's actually made? I mean, really made.
It usually starts with something called pig iron.
Right, churned out in these massive industrial titans known as blast furnaces.
And these aren't just giant ovens, they're incredibly sophisticated chemical reactors, really complex.
Absolutely. And today we're diving deep into one of the most, well, transformative innovations in their history, pulverized coal injection, or PCI.
Yeah, what's fascinating here is how PCI fundamentally altered the economics and efficiency of iron making. It's a prime example of continuous innovation.
Even in what might seem like a very traditional industry.
Exactly.
Yeah.
Our mission in this deep dive is to explore how PCI works,
Yeah.
the intricate science behind it, the ingenious ways operators manage its challenges.
And what it means for the future of making the very foundation of modern civilization. It's huge.
It really is.
You've provided us with some truly dense but incredibly rich source material.
A lot to get through.
Definitely. And we're going to extract the most important nuggets of knowledge to give you a shortcut to being truly well-informed on this fascinating topic.
Sounds good.
So let's start with the basics for you. Imagine a towering countercurrent flow reactor. Iron ore goes in the top.
Hot reducing gases rise from the bottom. Classic setup.
But the real magic, where the heat and reduction kickoff, happens near the bottom in areas called tuyeres.
Precisely. Through these two airs, hot blast air heated to around 1200 degrees Celsius.
Wow, that's hot.
Oh yeah, and often enriched with pure oxygen is injected. This burns descending incandescent coke, creating an intensely hot flame. We're talking typically 2000, 2200 degrees Celsius.
Incredible temperatures.
And this flame is hot enough to heat and reduce iron oxides throughout the furnace, and critically to melt the iron in the slag.
And that's where PCI enters the picture, right? Here's where it gets really interesting.
Indeed. Pulverized coal, or sometimes other hydrocarbons, are injected and combusted directly in front of these two ears.
So right into that super hot zone.
Exactly. The primary purpose of high-rate PCI is to significantly reduce the cost of producing pig iron
How does it do that?
by utilizing cheaper non-coking coal and extending the lifespan of valuable coke ovens. It's an economic driver, first and foremost.
And this isn't just some niche technique, is it?
Not at all. By 1998, all 30 Japanese blast furnaces were using PCI. Every single one.
That's market saturation.
Pretty much. The average ingestion rate then was 131.1 kilograms per ton of hot metal. But some furnaces, like Fukuyama 3BF, pushed it even further.
How far?
They reach rates as high as 266 kilograms per ton.
Wow. That really highlights the scale and the impact of this technology.
Absolutely. It was a game changer.
So what does this all mean for the coal itself? I mean, how does this pulverized coal actually combust in such an extreme environment?
Yeah, the combustion of coal is a complex process. It really is. It's assessed by parameters like its thermal value, its ash content.
Which tells you about the inert material and disposal needs.
Correct. And moisture, which affects the thermal value, and sulfur content, indicating potential emissions and corrosion issues.
Okay, standard stuff. But how does it ignite?
Well, the ignition of these coal particles can be a multi-stage process. It's quite interesting. Smaller particles, they heat up really quickly and ignite homogeneously.
Homogeneously, meaning
The volatile matter evolves strongly, and it sort of ignites all at once.
like a little puff.
Kind of. While larger particles, they tend to ignite heterogeneously with a slower temperature increase, more burning from the outside in.
That makes sense. But how do operators ensure it burns efficiently when it's shot into this massive furnace? It seems like control would be difficult.
Control is key. Combustion efficiency is highly dependent on having sufficient oxygen available.
Yeah.
And also the concentration of the PC particles themselves.
So you can't just blast it in there.
No, if the particles are too dense, oxygen can actually become deficient right where you need it, causing combustion to stagnate, fizzle out almost.
And that's where the lances come in, the injectors.
Exactly. Lance arrangements are so crucial. Experiments show that double lance arrangements, for instance, can significantly improve the dispersion of the pulverized coal particles.
Better spread.
Better spread, better mixing with the oxygen, leading to much better combustion efficiency compared to just using single lances.
What's fascinating here, too, is how the properties of the coke already in the furnace actually interact with the burning coal. It's not happening in isolation.
Absolutely. Even the type of coke influences the combustion focus in the raceway, that active zone near the two airs.
And you mentioned particle size. Can they really use coarser coal?
Surprisingly, yes. Stable operation can be achieved even with coarse coal particles, up to maybe 350 micrometers in size.
That seems quite large for pulverized.
It is, relatively speaking, but it suggests a robustness in the process under specific conditions. Operators need that flexibility.
And I imagine modeling plays a big part here.
Oh, extensively. Mathematical modeling is used constantly to understand and predict these complex flow and combustion behaviors. They break the process down into individual, understandable phenomena.
Makes sense. You have to model something this complex. So when you push the limits with high rates of PCI, new challenges inevitably emerge, right?
Always. You solve one problem, another pops up.
One that kept appearing in your sources was the generation of fines. What exactly are those, and why are they a problem?
Okay, so with increasing PCI, there's a significant rise in the generation of fines. These are essentially degraded coke particles and bits of unburnt char from the injected coal.
Little dusty bits.
Yeah, very fine particles. And they're problematic because they directly worsen key blast furnace operation variables,
Like what?
particularly gas permeability, how easily gas flows up through the furnace burden and burden distribution. They can also increase the pressure drop across the furnace.
So they essentially clog things up.
In a way, yes. They impede the smooth flow that the furnace relies on.
Any good news on how they tackle this? Any solutions?
Yes, definitely. For instance, at Fukuyama 4BF, they successfully reduced the fine coke fraction, even at a high PCI rate of 230 kilocalorie,
Ow!
primarily by improving the strength of the coke itself, making it less likely to break down.
Ah, so strengthening the existing material.
Precisely. And interestingly, unburnt char, despite being a fine, has a much greater specific surface area than coke.
More surface area.
Yeah, which means it's actually preferentially consumed by solution loss reactions within the furnace. It sort of reacts away more easily.
So it helps clean itself up to some extent?
To some degree, yes. It's not entirely negative.
Okay, what about the delicate balance of heat and temperature? It sounds like adding, well, cool pulverized coal could affect the furnace's overall thermal state.
You're absolutely right. That's a major consideration. The theoretical flame temperature at the 2-year nose generally tends to decrease with increasing PCI rate.
Which makes sense. You're adding cooler material.
Exactly. And that can affect the combustibility of the coal itself. It can lead to increased heat loss in the lower part of the blast furnace.
Which is bad for efficiency.
Right. But operators can modify this. They have levers to pull.
Such as?
They can increase oxygen enrichment in the blast air. More oxygen means a hotter flame, counteracting the cooling effect.
Okay.
Or they can work on suppressing peripheral gas flow, making the center of the furnace hotter through precise burden distribution control.
Let's unpack this further. The art of burden distribution. How important is it to control where materials fall inside that massive furnace?
Oh, it's absolutely critical. Crucial for managing gas flow and optimizing furnace performance.
How do they even do that? It's huge.
Modern furnaces use bellows top charging systems. These allow for very precise distribution of materials, coke, or fluxes across the furnace's throat, the top opening.
Like aiming different streams of material?
Sort of, yes. The choice of charging methods, like using a coke base first or an ore base first, directly impacts how the gas flows up through the material.
The goal.
The goal is generally to maintain a stable center flow of gas and inhibit excessive peripheral gas flow, preventing it from hugging the walls too much,
Why avoid the peripheral flow?
because that can lead to issues like channeling.
Channeling sounds like something you definitely want to avoid. What is it, and what happens when it occurs?
Channeling refers to localized, uncontrolled gas flows within the furnace. Imagine a fast river suddenly cutting a deep path through otherwise slower-moving water.
So gas finds an easy way up and bypasses other areas.
Exactly. It can be caused by various factors, incorrect operation, equipment defects, even fluctuations in furnace temperature.
And the consequences.
Prolonged or severe channeling can lead to significant problems, things like hearth accumulation buildup at the bottom, and even damage to the 2 years themselves.
That sounds serious.
They can be very serious. A compelling example from your sources describes a Chinese plant that experienced continuous peripheral channeling one September.
What happened?
They ended up with 44 burned out 2 years and 34 blast-offs, sudden pressure releases, in just a single month.
Wow. 44 2 years. That vividly illustrates the severe operational and production consequences. You lose that delicate balance, and things go wrong fast.
Very fast. Maintaining stable flow is paramount.
So beyond the core chemical reactions, a blast furnace is, as you said, a complex, almost living system. Let's talk about slag. It's not just a waste product, right?
Far from it. Slag is actually a vital component in the process.
How so?
It's carefully designed, chemically to remove gangue minerals, the unwanted rock, from the ore. It also removes ash from the coke and the injected fuels and other impurities like alkalis and sulfur.
So it's like the furnace's cleaning agent.
That's a good way to put it. Its
Yep.
composition is carefully controlled to ensure it has a suitable melting point or liquidus temperature, typically between 1300 and 1450 degrees C.
And viscosity, does that matter?
Hugely. It needs the right viscosity, usually in the range of zero point 0.2 to zero point 0.5 Pascal seconds, so it can flow out of the furnace easily during tapping.
And things like basicity.
The basicity of the slag, which is essentially its lime to silica ratio, directly impacts the sulfur and silicon content in the final hot metal. It's all interconnected chemistry.
Amazing how something we might just dismiss as industrial waste is actually an actively managed, crucial chemical component.
Absolutely. Nothing is wasted. Everything has a role.
What about the hearth, then? The very bottom of the furnace where all this molten iron and slag collect. Is it like the furnace's foundation?
It is indeed the foundation in many ways, and its integrity is paramount for a long furnace life or campaign.
How does it wear out? It must be under immense stress.
It deteriorates gradually over time. There are common wear patterns, like the descriptively named elephant foot wear near the bottom edge.
Elephant footwear. Okay, how do they monitor its health? You can't exactly look inside.
No, you can't. Operators use various techniques, traditionally drilling holes from the outside to estimate the remaining thickness of the refractory lining.
Sounds a bit crude.
It is, but effective. More advanced methods include ultrasonic pulse echo systems.
Like medical ultrasound.
Similar principle, these can even detect cracks or discontinuities within the refractory lining without stopping operations, which is a huge advantage.
And other factors.
Even the presence of trace elements, like lead, which can sometimes enter with the raw materials, can cause problems. Lead can lead to stress deformation and even pipe breakage in the cooling devices embedded in the hearth bottom.
So many things to watch out for. When damage does occur, how do they fix it without shutting down the whole operation for months? Tell us about fettling.
Fettling. It's a critical repair technique. It's essentially a form of in situ patching or protection.
How does it work?
It involves adding specific materials, often titanium-containing compounds like Ti-slag or T-ore, into the furnace charge, the materials going in the top.
So you add it with the regular feed.
Yes. These materials then work their way down and form a protective, often high melting point layer on the hearth wall where it's needed.
Creating a sort of scab or shield.
Exactly. It reduces the heat flux onto the wall and allows the underlying refractory to recover somewhat, or at least slows down further wear.
Does it really make a difference?
Oh, yes. For instance, the Xiang Steel No. 2 blast furnace managed to extend its campaign life by an impressive 11 years after successful titanium fettling operations.
11 years. That's incredible. Shows the long-term benefits.
Absolutely. This is a vital maintenance strategy.
That's truly ingenious. What other tricky operational problems do blast furnace operators constantly have to be on the lookout for? What's scaffolding?
Scaffolding refers to accretions or buildups that can form on the furnace walls, higher up than the hearth.
Like gunk sticking to the inside.
Pretty much. These buildups block the smooth descent of the burden, the layers of ore and coke.
And that causes...
That can lead to bridging, where the burden forms an arch over a void, or slipping, where a large chunk of stuck material suddenly drops down.
Neither sounds good.
No, they disrupt the process significantly. Operators detect scaffolding partly through unusual temperature patterns on the furnace shell.
How so?
The scaffolding area often shows up as being maybe 10-30 degrees C cooler on the outside shell because the buildup acts as an insulator.
Clever. Any other ways?
They also analyze stock rod records measurements of how the burden level inside is dropping. Erratic descent can indicate scaffolding or bridging,
And the countermeasures?
often involve adjusting the burden distribution, maybe directing more coke towards the walls in the affected area to try and scour it off or increase temperature locally.
Or more drastic measures?
In some cases, yes. They might even resort to carefully controlled blasting out of the accretions, though that carries its own risks.
It really is a constant battle against physics and chemistry inside there. Finally, let's talk about safety. These are enormous, high-temperature, high-pressure industrial processes. What are the biggest safety concerns for operators?
Well, arguably one of the most severe risks is gas explosion. The blast furnace gas itself is flammable.
What needs to happen for an explosion?
The prerequisites are very specific, thankfully.
Mm.
The gas concentration must be within a flammable range, typically something like 35–75% combustible components. Air, or oxygen, must somehow mix with this gas.
Creating an explosive mixture.
Precisely. And then an ignition source must be present. Hot surfaces, sparks.
Have there been major incidents?
Yes. Your sources describe a stark example from Capital Steel's number 3 blast furnace back in 1959. An explosion occurred at the dust catcher connection.
What was the damage?
It created a 10-square-meter hole and resulted in the loss of over 5,000 tons of hot metal production. It highlights the catastrophic potential.
A huge loss and incredibly dangerous.
Absolutely. Another major hazard is the contact between molten hot metal and water.
Because?
That can cause a violent steam explosion. Extremely dangerous. So water management and leak prevention are critical safety aspects.
So if we connect all this to the bigger picture, blast furnace operation is clearly this constant dance, isn't it? Balancing cost, production, safety, and increasingly environmental impact.
It really is.
What stands out to you about the future of this technology and that relentless drive for optimization?
The ongoing optimization efforts are truly impressive. Operators are always seeking to reduce coke rates, primarily due to its high cost and the environmental footprint of coke making.
While maximizing production.
While maximizing production, extending furnace life, and minimizing CO2 emissions, it's a multifaceted challenge, often with conflicting goals.
How do they balance these factors, especially with the complexities introduced by PCI? You mentioned the temperature drop, for example.
Right. With PCI, while it effectively reduces coke consumption, which is good for cost and potentially CO2.
There's a trade-off.
There's a trade-off. It influences the raceway flame temperature and the top gas temperature, as we discussed. Operators have to constantly optimize the PCI injection rate in conjunction with oxygen enrichment.
Finding the sweet spot.
Exactly. To keep these critical temperatures within acceptable ranges, maintaining both efficiency and stability, it's about operating within a defined window.
And looking further ahead, what's the next frontier in injectants? I've heard talk about hydrogen.
Hydrogen, yes. H2 injection is a very promising innovation, precisely because of these optimization goals.
How does it help?
Well, studies show that injecting 1 kilogram of hydrogen can potentially save approximately 2 kilograms of carbon in coke.
That's a significant saving. 2 to 1.
It is. It also helps to lower the oxygen and blast air requirement compared to some other injectants, so it hits multiple targets.
Efficiency and potentially lower carbon emissions.
That's the hope, making it a very attractive option for the future, although there are challenges with producing and handling hydrogen affordably at scale. But it's definitely a key area of research and development.
Wow, what a deep dive into the fascinating, complex world of blast furnaces and pulverized coal injection. It's incredible.
It really is.
From the micromechanisms of coal combustion happening in milliseconds
To the massive scale of hearth maintenance over decades.
it's clear that ironmaking is this high-stakes, highly engineered ballet of chemistry and physics.
Absolutely. It's an industry that continuously innovates. It has to. Adapting to new challenges, from cost pressures to environmental demands.
By pushing the boundaries of material science and process control.
The ingenuity involved in making something as seemingly simple as pig iron, the starting point for steel, truly is extraordinary when you look closely.
Exactly. So as you go about your day, maybe listening to this, perhaps consider the hidden complexities in the everyday objects around you, the steel in your car you're building.
There's a whole world behind it.
There really is.
Yeah.
What hidden depths, what surprising facts, what ingenious solutions are waiting for your next deep dive.